So far, in all of our annuity discussions and rate discussions, we've dealt with the idea in general of repaying a loan. And we're repaying principal and interest. But what we really haven't talked about is how the payment is dispersed. So when I make a payment, part of that payment is principal, part of that payment is interest. And depending on the way in which the loan is structured, I may be paying a certain fixed percentage in each direction. I may be paying all the interest up front. I may be paying principal afterwards. Well, there are lots of different schemes for this. The most common is called an amortization schedule. I'm very amused by this word personally because the root of amortization is mort. You're laying this to rest. Going to kill this loan eventually. We dealt with fixed payments, level payments throughout our annuities, but that's not required. We can do this a lot of different percent. Let's think about a simple example. We're going to borrow $1,000 at 10%. We're just going to do this compounded annually. So there's no conversion factor to work on at this point. And here's our payments are based on convenience. So at the end of year one, you pay $200. At the end of year two, you pay $500. At the end of year three, you pay the rest. So in an amortization of a loan, the lender gets paid first. So if I loaned you $1,000, let's walk through this a payment at a time. At time zero, you have $1,000 outstanding. A year later, what happens? But before that, you've had my money for a year. I'm going to charge you the interest. So I think of my balance now as $1,100 because I charge you the interest for the $1,000 you borrowed for a year, and then you make a payment. So please notice your balance at this point is only $900 because you paid the 100 in interest in addition, right? In one sense, this means you paid me the $100 for borrowing my money first, and then we applied what was left of your payment to the balance. Okay, another year goes by. My balance is that's after. So let's walk through each step, right? So my first is it's 900 times 1.1, which is 990. I then pay 500. And you're right, my balance is 490 at the end of year two. When time 3 rolls around, it says I'm going to pay the rest. How much is the rest? I'm sorry?
Right? You borrow 4,000.
But look at what my balance outstanding is. So how much do I owe at the end of the third year? I'm going to pay interest on that for another year, right? 490 times 1.1 is 539. So I'm going to end up paying substantially more, but when I pay the rest, my balance is 0. And I've laid my loan to rest. It's dead, Jim. This isn't truly a balloon payment because they weren't level in the middle. I can also do this as an equation of value. It said pay the rest, right? So let's figure out how to do this as an equation of value. If I'm going to do an equation of value, I need a time. I know exactly how much money I have at time 0, right? I have $1,000. So that would mean if I brought all the other payments to that time, I could compute the unknown amount based off of that. So at time 0, I have $1,000, and that's got to be the present value of all of the other payments. 200 brought back 1 year. 500 brought back 2 years, and our unknown amount brought back 3 years. If a time diagram would help, we can make one for this same process. Since my goal is to solve for k, I'm going to multiply everywhere by 1.1 to the third, which is the same thing, by the way, as making the valuation point time equals 3. And now I can solve for k directly. Let's see. 1,000 times 1.1 cubed is 1331. 1.1 squared is 121, so that's 424 plus 550 plus k. And if I rearrange, I get $539 again. Questions? My goal is to try and use all the other crap we already have for annuities, whether they're level or not, for equations of value, regardless of what our valuation point is. I want to try and use the stuff we already know how to do to make this work well. Let's generalize. So I'm going to take a loan amount at time 0 with an interest rate. I'll make my life easy. I per period. So I was using years, but we could use months, we could use weeks, it doesn't matter. I just want the appropriate equivalent rate. And I'm going to make payments throughout this time. They don't have to be the same, K1 through KN. I'll make N payments, but they're not all necessarily equal. The important thing here, though, is that I pay on the same time frame as my interest is computed. Is going to satisfy the same equation of value that we just came up with. The loan amount L is the present value of all of the payments. Since my payment period is matching my interest period, I don't have to worry about compound interest in the first period. If I'm just going to borrow this for one period, whether that's 1 week, 1 month, 1 year, I'm just going to make one payment and be done. So at the end of one period, I've paid one period's worth of interest. I give you all of that money back. Loan amount times 1 plus I, and I'm done. But if we go back to our example, I only made a $200 payment on a $1,000 loan, so there was still money outstanding. I still owed you more. I'm going to call that the outstanding balance. Sometimes it'll be called the outstanding principal. Which makes sense since that's the principal of our investment, the principal of our loan. Okay. I made one payment. The outstanding balance after payment 1 would be the loan amount having been charged interest minus the payment amount. Oh, wait a minute. This piece right here, LI. What's that? Oop, that should be a plus there. Sorry. What's that term represent? The interest I was charged in that first period. Notice that if I factor out a minus sign here, I can write this as L minus K1 minus L1, Li, right? Not L1, Li. That should be times I, not sub I. Let me write that better. L I. So that's my interest in that period. Okay, wait a second. This was outstanding balance at time one, and it started with our loan amount, right? And then we added on the interest and took away the payment. I'm going to rename some terms here. Instead of L, or equivalent to L, that's the outstanding balance at time zero. That's how much you owe at the very beginning, right? And then this Li, that's OB0 times I, I'm going to call that the interest in period one. And then this equation right here about OB1 is OB0 minus K1 minus, K1 minus Li, K1 minus I1. Hey, wait a second. This term, in terms of the example we did, you only owed $100 in interest, right? But you paid 200. So we took out the 100 for the interest and the other 100 went towards the outstanding balance. You repay part of the principal. So actually, that's what we're going to call this. We're going to call this the principal. I can spell. Principal repaid in this period. PR1. And then my formula just got a little simpler. It got a little simpler because I can say that OB1 is OB0 minus PR1. And I can iterate this process because now if I change OB1 to OB2, then it's OB1 minus PR2, and I do the same calculation for each of these. On page 159, we have a time diagram. We add on the interest, subtract the payment, that gives me the outstanding balance. Move to the next column, add on the interest, subtract the payment, gives me the outstanding balance, and we keep going until we've finished. All of these terms are defined in this box. But that's our time diagram. Now, I'm the first person to tell you that this entire scheme, because it is iterative, is best done on a computer. Rather than recalculate and recalculate and recalculate by hand. We can create a table and automate this. That table is called an amortization schedule. So let's think about the example we did. We had time. We have a payment at each time. We have the interest at each time. We have the principal repaid at each time. And then we have the outstanding balance at that time. So these 5 columns make up the foundation for an amortization schedule every single time. And the formula we're going to use is this set right here. That's what I'm going to use every time. The example we did, what was our loan amount? $1,000. So at time 0, we hadn't made a payment, we hadn't been charged any interest, we hadn't paid any principal. We had a balance of $1,000. And our rate, what was our rate on this problem? Okay, so at 1 year, we made a payment of $200. The interest is outstanding balance times the interest rate. The interest is $100. Notice that's simple interest on 1 period. P times R. That's all I need. 1,000 times 10%. How much principal did I pay? Oh, take 200, take away 100. I paid $100 in principal. Subtract that from the 1,000. My outstanding balance is 900. At the end of year 2, we made a payment of $500. The interest was 90. Subtract 500 minus 90, you get 410. Subtract 410 from 900, you get 490. Now, here's where I have to do things a little bit backwards because it said pay the rest. I want this to be 0. Oh, okay. The interest I will be charged is $49, right? I want the principal repaid to be all 490 so that I end up with a balance of 0. That tells me what this payment is. It's 490 plus 49 or $539. I am the kind of guy who does exactly this in Excel. There. That's the wrong one. Stop. That's the wrong one. 3, 2, 3, 4. Where did I put chapter 1 example? There it is, example payment schedule. Haha. There. And I put this up on Canvas. But notice, all I'm doing is I'm multiplying the interest rate times the outstanding balance from the previous line. If I hit enter on this, you'll see it's highlighting those two things. That's all I'm doing is a simple interest calculation. And then mechanically, I'm adding and subtracting. That's it. This is the boring part of an accounting job. Those of you who like Christmas, this is Bob Cratchit's job. He's a clerk in the lending office. His job is to write schedules for all the different loans they have. And that's why he's sitting there writing and calculating all day long. Now, because I'd worked out in advance, I knew what this last payment was. I can work this through. I can generalize this. Let's think about what happens in general. Come on, stay up there. I'm going to have the same columns. T, KT, IT, PRT, OBT. I will have my loan amount, OB0. I'll make, at time 1, some payment. The interest, I1, will be OB0 times I. The principal repaid at time 1 is the payment minus the interest. And OB1 is OB0 minus PR1. Keep going. At time 2, we make a payment. The interest is OB1 times I. Principal repaid at time 2 is K2 minus I2. OB2 is OB1 minus, it's OB1 minus PR2. And so on. Until we lay our loan to rest. The general form of an amortization schedule is on page 160. Over and over and over, we do exactly the same calculation. I will point out to you, there is a typo in the textbook. On page 160, they wrote in the principal repaid column, they wrote K1 minus L1 and K2 minus L2. There is no L1 or L2. There's only one loan amount, L. So that should be I1 and I2. It's just a typo. They did fix it down here in the general version, but they screwed it up on the first 2 lines. So please make a note on page 160, that's a mistake. Oop, back out of page. There, oh, come on. There we go. I keep going. I make a payment. Interest at T plus 1 is OBT times I. Principal repaid at T plus 1 is KT plus 1 minus IT plus 1. And the result is OBT plus 1 being OBT minus PRT plus 1. Eventually, I will finish this loan after some number of payments. And ideally, this balance will be zero. I'm going to use a subscript T, okay, capital T, to represent the sum of all of my payments. I'm going to do IT the same way. Oh, I should use a J here because we have an interest rate I. I don't want to use the same variable more than once. Oh, wait a second. This is the total I paid. This is the total interest. But IJ, is generated here. That's I times OBJ. Let's do an example where I don't know the payment. How can I go figure out the payment? I am going to make a loan, $1,000. My lendee is going to pay me back over 6 months at 12% APR, and we're going to make payments at the end of every month. Payments for the first 3 months are low, and then they double for the next 3 months. So you're going to pay whatever you're going to pay for the first 3 months, then you're going to double that for the next 3 months. How much are we paying? Each month. And once we've figured that out, let's make a schedule. Fortunately for me, figuring out how much to pay is an equation of value. So let's go through the exact same setup that we just did. I'm going to make a payment for 3 months of X. I'm going to make a payment for the following 3 months at 2X. So how do I set this up for my equation of value?
V from X times V plus V1 plus two.
X times V plus,
X V2 X V3 2X V4 2X V5 When I said it like that, I'm like taking the comment.
okay, well, I'm fine with that, X, but you said V, V1, V2, and that's why I was confused.
Oh, okay,
So V plus V squared plus V cubed plus 2X, V to the fourth, V to the fifth, V to the sixth. What's that equal to, though? That's just an expression. What's that equal to?
oh, more of the one plus five.
That's what V is equal to. What's this whole thing equal to? Remember, my goal is to make an equation of value. I need an equation that's got to be equal to something. It would be 1,000. This is the present value of all of the payments, right? The present value of all the payments should be the loan amount. And now my brain goes, wait a second, I've seen this expression before. V plus V squared plus V cubed. V plus V squared plus V cubed all the way up to V to the n, that's my present value factor. So this right here is X times A3. What's the interest rate? Because it's 12% annually, but I'm converting to monthly. Yes. Plus 2X. Hey, wait a minute. If I write V cubed, then this will be V squared, V to the third, won't it? Beautiful. I now have an expression where I can figure out all the numbers, factor out an X, and I get A301 plus 2, 1.01 to the negative third times A3.01 equals 1,000. Now I just have to know what those numbers are in the middle. How do I do A301 again?
One minus B to the end, so 1 yep, yep.
So now I grab my calculator and I figure out what this number is. One minus 1.01 raised to the negative 3 divided by 0.01. I'm going to store this number. Store that under A. That way I have it. So that goes here and here. 2 times 1.01 to the negative third times A. That's this whole expression here. Add another A to it. That adds on this. That's the number in parentheses. So I divide 1,000 by this. 1,000 divided by this number. There you go. That's X. If we round, we'll call that 115.61. Ready for a schedule? T, K, T, I, T, P, R, T, O, B, T. What time is it? Payment, interest, principal repaid, outstanding balance. I start with an outstanding balance of $1,000. My first payment is $115.61. How much interest do I owe at the end of the first month? It's 1% of this outstanding balance. Subtract 105.61 is how much I'm going to put towards principal. Subtract from 1,000, and I get 894.39. Yes. Repeat the process. Payment 2 is $115.61. But the interest I owe this time is 1% of this, $8.94. By the way, a bank is more than willing to round up, no matter what the decimals are, to charge you that extra penny, or round down when they have to pay you the extra penny. But we're going to round the way we're supposed to. Okay, subtract. What is my principal repayment here? Subtract those two. 106.67. Subtract those two. One more time. Payment number 3, $115.61. The interest, 7/8. Okay, this time it should be 788 if I round appropriately. Subtract 115 minus 100, 107 plus 12, 107, 73. Subtract again. Now, I'm about to disagree with the textbook. My payments double. If I double my payment, 231.21, right? If I double my payment, should be 231.22, shouldn't it? So the textbook does 21. I'm going to do 22 because I'm doubling this amount. And I work in pennies, not fractions of pennies most of the time. So payment 4 is 231.22. The interest I owe, yeah, it should be 680 because we're going to have 7,999. So 231.22 minus 680 is 224.42. 679.99 minus 224.42 is 455.57. Payment 5. My interest this time is $4.56. 231.22 minus 456. Oh, wait a minute. Yes. Is 226.66. 228.91. Now here's an interesting point. Payment number 6, 231.22. Interest. What's the interest this time?
Two.
So my principal paid is 228.93. My balance is negative 0.02. My last payment really should get adjusted. It should be adjusted so that I end up balancing this out perfectly. I should really underpay this by 2 cents to balance it. But if I actually make the payments exactly as scheduled, then the bank is going to call me back and go, here's your 2 cents back. What did I pay total for these two columns? What's my total payment made? My total interest paid. Add these up. Given my rounding change, I take one of these and one of these and then multiply by 3. That's $1,040.49. And my total interest is therefore 40.49. Although technically, my total principal repaid is 1,000 plus 2 cents. That's because that's why I'm over here by a little bit. The textbook used 231.21 and thus came up 1 cent short at the end. So they would make a final payment that was 1 penny higher rather than 1 penny or 2 pennies lower. Questions? What are you doing? I hit the wrong button. Come back to me. There we go. Here it is the way the book did it, with that last payment adjusted by 1 penny to give me a balance of 0. This example's on Canvas. Will you stop that? Questions? Let's think about this column, this outstanding balance column. OB1 is OB0 times 1 plus I minus the first payment. That's the formula we came up with. OB2 is OB1 times 1 plus I minus K2. Oh, wait a minute. Let's replace OB1 with this. Notice if I distribute OB0, 1 plus I squared, minus K1, 1 plus I, minus K2. OB3, let's keep going. OB3 is OB2 times 1 plus I minus K3. If I replace OB2 with all of this, that's all multiplied by 1 plus I. Then I subtract K3. That's OB0, 1 plus I to the third, minus K1, 1 plus I squared, minus K2, 1 plus I, minus K3. I've got what looks like a geometric series going on here in terms of all of these other pieces being multiplied by decreasing powers. OBT is going to be OB0, 1 plus I to the t, minus K1, 1 plus I to the t minus 1, K2, 1 plus I to the t minus 2, K3, 1 plus I to the t minus 3, all the way down to K, t minus, K, t minus 1, 1 plus I, minus KT. That should be a minus sign there. Or if I write it as a summation, OB0, 1 plus I to the t minus the sum, L goes from 1 to t, KL, 1 plus I to the t minus L. Okay, what the hell is this formula for OBT? In terms of our schedule, our big, ugly, nasty schedule here, what this is doing is it's bringing everything forward in time. Our valuation point is brought forward to time t. In other words, I'm standing at time t and I'm looking back at all the payments we've already made and I'm taking their future value. That's why all of these are raised to positive powers. I'm taking the future value of all of those payments and subtracting them off. I'm looking backwards in time to do this. This is future value. But I'm looking at the past. I'm looking back from time t. Page 162 shows a timeline diagram that I think is pretty helpful in this case. What I've done is I've brought everything that was before time t up to time t. And I'm saying all of these, this is the loan balance. These are all the payments I've made. Subtract those off, and we get the balance outstanding today. Because I'm looking back, we're going to call this a retrospective. By the way, this actually shows me the valuation equation we were using. Because if I make this entire set of payments, then what does this become? If I pay off the loan in n payments, then OBN is 0. And that will be OB0, 1 plus I to the n, using this retrospective form, minus sum L equals 1 to n, KL 1 plus I to the T minus L, but that's equal to 0. So if I move this to the other side, I get OB0, 1 plus I to the n equals the sum KL 1 plus I to the T minus L. L goes from 1 to n. This expression right here is the equation of value at time n, as opposed to at time 0. The future value of the loan is the sum of all of the payments we made. And that goes with what I said up there under the box, is that these were all the future values of the past payments. So I really am looking back from my furthest future point to do this equation of value. By the way, if I multiply both sides by 1 plus I to the negative n, I get the valuation at time 0. Questions? So what if instead of using future value, I used present value? Well, that would mean I need to take all the payments that are coming up and bring them back to today. So let's think about this timeline here. Here's where I am right now. Here are all the payments coming. All right. Same idea. If I do my valuation right here, then this is the amount, and it's equal to the sum of all the payments to come. I have to back that up that many spaces. Oop, sorry, t minus n. I realize I wrote it the other way in my notes. T plus 1, 1 plus I to the minus 1, kt plus 2, 1 plus I to the negative 2. And that's why I have kn 1 plus I to the n minus t. So if I'm bringing the present, the future payments back to today, I'm looking forward in time to figure out today's value. I'm looking at the things that are going to come in the future. This is called the prospective method for finding OBT because I'm looking forward, prospect versus retrospect. This is more useful when I know the payments to be made at all future and past points. So for level or non-level annuities, this is actually very useful. Questions? Let's tweak some numbers then. What happens if over the course of the loan, things change? We've already seen what happens if my payment changes. I can adjust it in the schedule. What if the rate changes? This is what is going on today. Remember that just a couple weeks ago, the Federal Reserve lowered their primary interest rate. If they lowered their primary interest rate, that should trickle out to all of the other interest rates. So your credit card interest rate should go down. Your adjustable rate mortgage should go down. Any loan or credit line you've got outstanding with a bank should have its interest rate lowered slowly over the course of the next 2 to 3 months. Those rates should all drop, not by a lot, but by some. Problem is that banks are still paying interest and they haven't lowered those rates either. So there's a chase here going on. If the interest rate changes, I can adjust the payments to reflect this. Let's take our $1,000 loan. And we're going to do 6 monthly payments. But the first 3 payments are going to be at 12%. The second 3 payments are going to be twice as much, but we're going to change the rate from 12% to 6%. The first thing I need is to find X. So I need to build my equation of value. just like the last one. I can set up the equation of value based on today. So, Maria, let's walk through this the way you set it up before. First payment, second payment, third payment, fourth payment. Wait a second, I have a problem here. I've got two different rates. This payment was made at an interest rate of 0.01. This one is 0.005. Oh, hang on. It's only charged that interest in the month 4. So you'll notice I didn't raise that to a fourth power. What was it charged for the previous 3 months? It was charged this interest, right? There are two different V's here. The first 3 months, I got to bring that back through this point. These are at 12%. These are at 6%. I got to remember that I change interest when I go here. 2x V.005, 2 months, V.01 cubed. And then my last payment, V.005 cubed, V.01 cubed. I'm going to do the factoring out here. And when I do the factoring out here, I get V.01 plus V.01 squared plus V.01 cubed. Here, I get 2x V.01 cubed and then V.005 plus V.005 squared plus V.005 cubed. So I actually have to do two different interest rates to do this problem. So this is going to be A 3.01. This one's going to be 1.01 to the negative third, but then it's A 3.005, not 0.01. Give me a number. We got to figure out what X is. This is the same number I stored before, right? This 1.03, A 3.01. That's 1 minus 1.0301 to the negative 3 over 0.01. We did that number already. This, on the other hand, this is a new number. So this is the number we had before. This is 2.940985,207. I wrote all those decimals down last time because I stored that in A. So now I have to work out this number. Two times 1.01 to the negative third times 1 minus 1.005 to the negative third divided by 0.005. 5.7657871159. Those, I add those two numbers together, so I add A to that. And I get X times 8.706772367. So X is divide 1,000 by that number, $114.85. Well, technically it's 85.3 cents. I'll round down for the moment. That means I'm going to double that after 3 months, because we make our second set of payments twice as much. Twice as much. Okay, again, now I've got a problem. If I didn't round, then when I double the payments, I should get 229.71, not 70. If I round, it'll be 70. So it's going to depend on where you want to round as to what your payment license is going to be. Again, I think that's this one. Nope. Yes, it's this one. Here we go. There are my payments, 114.85 for the first 3 months. But notice here is my interest rate change. So all the calculations from this line down calculate the interest using the new rate as opposed to the line above, which calculates the interest using the old rate. See which block is highlighted. So to calculate the interest rate for the first set of payments, I'm using the interest rate that's at the top. To calculate the interest rates for the next set of payments, I'm using the interest rate that's off to the side. You can adjust the interest rate however many times you want, however often you want, depending on what the loan is entitled to. Adjustable rate mortgages do exactly this. Depending on the type of mortgage, you can have adjustable rate mortgages that adjust twice a year, every 6 months, once a year, once every 2 years. It's up to the loan designation. But this is a not uncommon procedure. Again, notice if we hadn't rounded, there might be a slight difference in the way we make the payoff. At the end, we might be off by a couple of cents. You'll see this frequently. Your last payment is almost always drop adjusted or balloon adjusted to accommodate for the missing pennies along the way. Questions? You are reminded that Chapter 2 is due on Thursday. I will see you all then. I hope you have a wonderful rest of your day.